Good afternoon and welcome to this week's episode of the CERIAS Security Seminar. Today we have a guest speaker who's had a wonderful, a number of meetings with some of our faculty on campus and excited about the collaborations that could come out of that. For those who are watching on video, please take a look at the CERIAS website as the 20th Annual CERIAS Security Symposium will be coming up April 9th and 10th of this year. And if you happen to be viewing this in the future, take a look at our website because annually we hold this event that is open to the public. So our speaker today is Professor Meng Yu from Roosevelt University. Welcome, Professor.
Okay, thank you. Okay, thanks for coming, everyone. And it's my great honor to report my recent research work to professors, students here. So hopefully I can get some feedback from you and further improve our research work. In recent years, our research group mainly worked on ARM processors and also security problems on ARM-based devices. So the major reason is the popular IoT devices and edge computing, Internet of Things, cloud computing. So the recent computing trend, those major trends will bring in more and more ARM-based devices. So the security problems are becoming a very important issue on those devices. So we have worked on several security problems. One of them we think is very challenging is how to protect the applications when the operating system is compromised. So basically, you can think about the challenging problem. I'm thinking my career. So I think more than 10 years ago, when I first heard of challenging security problems, one of the problems is how to run our programs in a malicious environment or in a hostile environment. How can you guarantee your program, your app is okay in that hostile environment? So this question or this problem has not been changed. In the past decades, we proposed a lot of solutions, but it's still a challenging problem. So today, we just pick this particular problem. We talk about one possible solution on ARM processors. Okay, so that's the whole background. So why we pick ARM processors? So basically, it's mainly about the recent trend, especially if you go to Home Depot, Walmart, or Lowe's, so Best Buy, those popular stores, you will see smart home demo area. So you go to that area, you see a lot of smart things, like the Arlo or smart doorbell, smart switches. So those are all Internet of Things. So I think every one of us already learned a lot of it, and they are becoming more and more popular in our daily life. Like it or not, when I look at my home routers, I see 30 or more devices connected, including the Chromebook issued by my kids, like elementary school and middle school. So everyone has more and more devices. Those devices are mainly based on ARM processors. Okay, so this is the major trend. So if we look at this picture, so this picture is from the internet. So I didn't make it. So I borrowed this picture, and this picture shows the family of Internet of Things or smart devices. And you see how many categories, how many different Internet of Things or smart devices we are having now, and we are having more and more of them in our daily life. Okay. So this picture, you see a lot of movies recently, right? So sci-fi movies. So the robots are becoming smarter and smarter. We are fighting with them. So a lot of people are really worrying about what our future will be if they are getting smarter and smarter, especially security plus the recent advance or development of AI technology, right? So someday probably the robot may beat us. So if we don't act quickly, so that's the one view of Internet of Things or smart devices. But this picture is more realistic. This is not in like movie. So this is a real thing. So many years ago, not many, like 5 or 6 years ago, the first vehicle was hacked, is Jeep. So the Jeep was hacked. It's by a researcher, fortunately not by the real hacker. The researcher hacked the Jeep and steering the Jeep into like off the road. And also the researcher demonstrated how to shut off the engine when the Jeep is running on the highway. So it's very dangerous. So those are real threats to our real life. And recently, Tesla, this is a very popular name, right? A lot of young people, they are considering Tesla as their first car ever. So that's a big trend. So Tesla was also hacked, okay? So because the whole vehicle has a lot of smart devices, and the more computer or the more processors you bring into the system, the more vulnerabilities, more threats we have to face. So that's very realistic problems. So if we look at the platform, so what are supporting those IoT devices or smart vehicles or smart things? Then most of them, I'm not saying everything, but most of them are using ARM plus Linux platform. Or even if they're not Linux, in some kind of Linux or customized Linux. So that's the major platform supporting the Internet of Things or supporting the smart devices or smart vehicles. That's why we pay great attention to the security problems of these devices. So this platform, if you look at the list here, these platforms are supporting so many devices, like digital video recorders, IP cameras, like RO system, a lot of monitoring system, Chromebooks. So my kids bring home Chromebooks issued by their schools. I didn't buy them, but they are bringing Chromebooks home. And also smartphone, Android systems, even iPhone. So iPhone is not using Linux, but iPhone is using like similar technology, sharing the similar vulnerabilities I'm talking about here. So those are the platform being used by many IoT devices, smart devices, and we are looking at those platforms and see what we can do to improve the securities. So this figure shows basically how many problems are being discovered in each year, and the trend of those vulnerabilities. And next slides summarize the major problems. So if we have security breach on those platforms, because they are serving like mission critical or life supporting devices, like medical devices. If the medical devices is using ARM plus Linux platform, they're compromised, then that's life supporting system. So that's life threatening problems. So for smart vehicle, it can also be life threatening problems. So the major threats we're talking about here will be once the system is compromised, the sensitive data is gone. Then once the kernel is compromised, all the data on the device is gone. So think about the smartphone as an example. I'm using my smartphone for like health data, sensor data, and also my bank accounts. So a lot of like sensitive data and the critical applications in my life. The solutions. So now we think about smartphone as an example. Think about smartphone as an example. If I worry about the app I'm using, for example, Chase Bank account, so Chase Bank app, or UA app. So I'm using UA app to purchase air tickets. So it will be connected to my credit card. Anyway, so if I'm using this app on the platform, so it's automatic. So on the platform compromised, that there is no way I can protect the sensitive data, okay? Because think about the operating system. If the operating system is compromised, then there is no security for apps. There is no privacy for apps. Operating system is serving as the manager or serving as the god of the whole computer system. Once the kernel is compromised, no secret is hidden, right? So all users' privacy is exposed. then all control flows can be modified. So that's a huge problem. So there are existing solutions. So if you're working in security area, probably you have heard like overshadow, ink tag. Those are the popular solutions. I mean, there are 2 examples of the popular solutions. There are like more than 10 solutions. Okay, so these solutions are proposed. If you look at the right top, the figure shows the major ideas how to protect the compromised operating system. So isolate the damage from the compromised operating system, to the applications, because we want to protect the applications in the situation when the operating system kernel is compromised. That's the goal, okay? So basically you can see here, we have here some solutions. You see the right top of the slides. So we can think about the virtualization. So the virtualization idea runs a hypervisor below the operating system. Okay, so that's how we use cloud services. So if you rent Amazon EC2 services, you rent a virtual machine, but your virtual machine is running on top of a hypervisor. Okay, so that's the cloud structure, or we call it virtualization structure. So that's great. So basically, if you think about that structure, now we have layered software stacks. So even if the operating system kernel is compromised, it's still good. We still have a hypervisor below the operating system. Okay. So as long as the hypervisor is not compromised, we have something, okay, with higher privilege level than the operating system kernel to manage everything. Okay, we're still good. So that's the goal, or that's the main idea of protection. So as long as we have something with higher privilege level than the operating system kernel, we're good. Okay, so basically that's the key idea of so let's go back, of recent proposed technology. So virtualized running environment, we run the guest operating system. If the guest operating system is compromised, we have the hypervisor, so the hypervisor can protect the application in the compromised operating system. That's the key idea, okay? So any questions? Okay, so the idea is very simple, and many approaches are sharing exactly the same idea, but using different implementations or using different implementation details, okay? So that's the major work in recent years. For example, overshadow is one of the very popular solution using hypervisor to protect the applications against compromised kernel. So even better. So if you look at here, Intel SGX, this is a very hot term in recent years. SGX provide hardware protection. So the processor has included additional hardware, okay? So building it's called isolated hardware area in the memory. So even if other part of memory is compromised, the isolated part will be untouched, okay? So that's the idea of SGX. Basically, we don't use hypervisor, but we use hardware, additional hardware. So basically, the earliest paper of SGX was published as with title Heaven. It was in OSDI 2014. So that's the earliest idea using SGX. SGX becomes very popular, but the requirement will be the processor has to support SGX. And another problem, we don't talk about too much about that problem today, but just reminder, we still have the side channel problem for SGX. So basically, when you enter SGX, you leave something in the cache. When you get out, then may you try to utilize the information left in the cache. So it can create a side channel for the attackers. So it is still not the perfect solution, but it is much better. So basically, I'm talking about, okay, hypervisor-based solution or hardware-based solution, and the third category, split, okay? So if I want to protect application, then how about we build the application differently or in different ways from other regular applications. So like you're building an additional shell, additional protection mechanism into the application. That's the third way. So basically, these are the three major categories to support the protection, okay, of application against compromised operating systems. That's the existing solutions. So the problem of the existing solution is most of them are based on Intel platform or Intel architecture. So Intel architecture is being used by Intel, AMD, and many other like server manufacturer. They use this platform, okay? But for mobile device, like I said, it's ARM. ARM doesn't have SGX. When ARM was built, it doesn't support hypervisor, okay? So now it supports, but we have to port the hypervisor idea onto the ARM platform. So we don't know whether we can do that. And it's also a very heavy solution running on the ARM. Think about the hypervisor. If you are installing a virtualization platform like VirtualBox, okay, VMware on your laptop running a virtual machine, it will be much slower, okay? So it will significantly affect the performance of your personal computer. So it's not a solution for high performance computing, or basically if we bring in the hypervisor idea onto mobile devices, then it may be too slow for smartphones or for smart devices, okay? Especially think about the smart switch. How can we have a hypervisor on smart switch? That's too heavy. So not a good solution. So basically here, the proposed solution is like, we call it trust shadow. We build a protected application area on the ARM processor. So it's called a shadow area. So we trust that area. So we protect that area against the normal operating system. So this project is collaboration efforts between Microsoft Research, UTSA. I was from UTSA. I just moved to Roosevelt last fall. So this work was done when I was at UTSA, and also Penn State, Florida Institute of Technology. We worked together to develop this idea and implement the system on ARM processors. So we want to support the applications without any changes, modifications, because that's important. If we want to change the applications, then our protection will have very limited applications. So then the vendors or the software developer, they need to change their application to adopt our structure or technology. So that's a lot of effort. So basically we are saying, okay, our protection should not require any changes to the existing application. And also we want to use existing operating system. We don't want to change anything to the operating system, okay? So we want to use existing application, existing operating system. So basically it's very easy to be adopted on the existing mobile platforms. So before we go to the full technical details or complete solutions, let's look at the background of ARM processors. So in case you don't work on these areas, so probably you are working on AI, so this picture will give you some background, okay? So how the ARM processor looks like and how much difference it is from the Intel processors, okay? So here, the ARM processor, so this figure is mainly for ARM Cortex A series. So ARM has two series. So Cortex A is for mobile devices. Cortex M has less computing function, less powerful computing power. Then Cortex M is usually for devices, like not that smart. So Cortex A is usually for mobile devices, still doing some computing, doing some graphical things. So here, this figure shows, this is the structure for both Cortex A and Cortex M. But if you look at the details, we mainly use this structure for Cortex A, because Cortex A has more powerful processor than Cortex M. So basically, if you look at the red color here, the red line here, divide the processor mode into two separate world. We call it world. So the red part in green color, you see that's a secure world. Okay. So in secure world, the change of memory can be anywhere. Of the processor connected memory space. But in the normal world, the access to the memory is limited. So now think about a computer using ARM processor like Chromebook. Okay, so for the whole memory space, some space can only be accessed by the secure world. Okay, but all memory space, if the secure world configure allows, all space can be accessed by the processor from the secure world. But the normal world can have very limited access. Okay, they are not allowed. If the processor is in normal world, the processor cannot have all access permissions to all the locations of memory. So limited access. So that's the permission designed by the ARM processor. So basically, when we enter the secure world, we can do everything we want. If we go back to the normal world, we have very limited functions. Okay, so that's the short summary of it. So given this security design in a normal world, if you look at the devil in red color here, this devil means, okay, the operating system kernel is compromised. Okay, so in the normal world, we have operating system kernel compromised by the attacker already. Okay, so basically, if the attacker is here in the normal world, like I said before, the attacker cannot access the secure world. Okay, so the damage will be restricted to the normal world only. Okay, so that's the hardware design by the ARM processor. So here on the right side, if we have a trusted component like trusted OS, here I'm writing trusted OS here, but later on I will explain it's really not a complete OS. We don't run two operating systems here. So this trusted OS just show it serves the operating system function, but we really don't have two operating systems here. Okay, so think about the right side. So if in the secure world, the attacker compromised any component, then the whole platform is gone. Okay, that's the situation we do not want it to happen. Okay, so basically here, given this figure, I'm seeing the hardware supports a secure isolation between the secure world and normal world. If anything bad happens to the system, we want the bad thing to be isolated, to be contained to the left part, to the blue part. Okay, so that's it. That's the goal. So given this hardware support, now we can think about some possible solutions. So very straightforward. Okay, so the secure world sounds really good. Okay, so anything we put in the secure world, it will not be touched or accessed by the attacker. Okay, that's really good. So why don't we put the operating system and the applications, everything into the secure world? Then nobody can touch it. All of them are protected. Can anyone tell me, why don't we do that? So does that sound a very straightforward solution, and then the problem all solved? Why not? Yes?
Because we need to install applications that will change OS.
Oh, I can repeat. So basically, he is saying we install the application to the secure world, we're going to change the application design, right? That's your point.
Yeah, that operating system state will change if we install application.
Okay, so basically the installation of application will also change the operating system, right? Yeah, that's a very good point. So basically he's saying, okay, when we try to bring everything to the secure world, actually we already changed the application operating system there, right? Very good point. So basically, he's absolutely correct. And think about if we are moving everything to the secure world, or in other words, secure room. We think this room is isolated, this is trusted room. Then we bring everyone here, then this room will be secure? Actually not. Probably we bring in some bad people here, right? I'm not saying you're bad people, but when we bring in everything here, everything to the secure world, we are bringing in risks, problems, everything we are bringing to the secure world, okay? So that's against our initial goal. We cannot do that. So we must leave untrusted component to the normal world. We only bring in trusted component to the secure world. That's what we can do about it, okay? So another comment. For operating system, we absolutely don't want to move any operating system, the whole operating system, into the secure world. What's the reason of that? So for software engineering perspective, for security perspective, any operating system, I mean, except the customized operating system, or especially developed operating system like SL4, most operating systems, they are too large to secure. They have several millions lines of code. There is no way to make sure they are vulnerability free, they're absolutely secure, no way to do that. So we cannot move the whole operating system into the secure world because we are bringing in all the problems to the secure world, okay? So that's why it's not a simple or straightforward solution. So we cannot move everything there. We can only move what we want to protect there. So only trusted applications, okay? So here, this solution, basically, okay, so you bring the first point, so can't protect the legacy code, okay? So if we want to move operating system there, application there must be some changes, either to the operating system or to the application, right? Very good point. So that's the first thing. We cannot move everything in the secure world. And also additionally, like I said, too large to secure. And also doesn't support memory encryption. So I expand this later because, so currently you can think about once when we access, once the kernel is compromised and the kernel can access anywhere it can access. Okay, so like in the normal world, the kernel can access all space in the normal world. So if we have trusted data in the normal world, it will be disclosed to the attacker. Okay, so if we have compromised kernel in the secure world, it will be disclosed to the whole computer platform. So that's the problem. So let's see. Let's look at this figure first, then we go back to the summary. Okay, so this figure shows, you can see here. Okay, so we only move trusted application to the secure world. Okay, then you see here at the bottom of the trusted application, the previous figure shows the complete operating system, secure operating system. But here, like I said, complete operating system is too large to be brought in here. Okay, we only have a runtime system. So now think about the runtime system as very small component. Is a proxy. It's just a forward. So okay, so if you're making a system call, let's say so as a computer science major or other major, as long as you do programming, a system call, you will know here. So applications will make a system call, right? Open file, close file, or send message here, system call. Then this runtime system will serve as proxy. Okay, it's not a complete operating system, but it serves as proxy. You see here, forward the request to the kernel outside the secure world. So basically, I don't trust the kernel, but I trust the runtime system. So please forward my service request, then the service will be done by the kernel outside the secure world, so in the normal world, okay? So this is the key idea how we solve the problem. But now I have a question for you. So not that simple. So looks like problem solved. So my question will be, okay, so every application will make a lot of system calls, right? So anyway, I'm not saying we do all the system calls here, because as said already, we don't have a complete operating system in the secure world. So now all the work, or most of work, will still be done outside the secure world. So here, Linux kernel. But I'm marking the kernel as compromised. So you may ask, what are you saying there? You're still sending the work to a compromised kernel. Then how the job can be done? What do you think? Can you think about it? So I'm sending a job to a person I don't trust. Okay? So it's possible, like I said, open the file. Then this compromised kernel will not open file. Okay? But he tells me, I open the file for you, but actually not. Okay? What if it happens? That's okay. That's okay. So I don't care. So the protection goal here is I don't want to guarantee a compromised kernel still do the job. I don't care whether it does its job. I only care my application here. My application is protected. So in the case of a compromised kernel, my information is not disclosed. That's it. That's my goal. I don't guarantee the functionality of the kernel. But in the case of a compromised kernel, I want security. I want confidentiality. I want integrity. Okay? So that's my security goal. So basically, this is the protection structure. So basically, okay, I want to do some system call. I send the system call to runtime system. Then this proxy will forward my request to the kernel. Okay? So regardless, the kernel is compromised or not, is doing the job or not, I don't care. Okay? You need to do the job. Do it or not, reply. That's it. Okay? So that's the protection. But in the case, now we look at the figure again. So in the case that the kernel is compromised, you see here, the kernel is compromised. It's different from existing system. It's different from any existing platform. This kernel can only access normal world. Okay? So this kernel cannot access anything inside the secure world. Then that's it. That's our goal. That's the goal of our design. Okay? So it cannot steal anything from our app. It cannot do anything to harm the integrity of our application. That's it. My social security number is protected. My bank account is protected. My transaction is protected. That's the goal. So in case of a compromised operating system, my app is protected. That's it. Okay? Any questions? Yes.
So where is the runtime system actually? Is it running in like a kernel mode state? Like where it has like secure, like a lot of power to like operating power, or what? How does that work?
Okay, let me repeat your question. So he asked, where is the runtime system? Running here, and how basically you're also asking how the services are done, like in addition to the kernel functions, what are the processor mode, and what are the privilege levels, right? Mm-hmm. Yeah, very good question. So I'm going to show you in next slide.
Okay.
Very good question. So you must be in this field. Okay, very good. So let's go back to look at the quick summary. So we have limited time. So a quick summary of our design goal. So basically, we want isolation. Okay? So we want a strong isolation using the hardware facility to isolate our applications from the compromised operating system. Secondly, we want to reduce the trusted computing base. So this is important. Like I said, there is no way to secure the whole operating system. That's too large, several billion lines of code. So now we want to reduce the TCP. We will only guarantee runtime support, the proxy. if we secure the proxy has only 5,000 lines of code. So in our development, so that's a small amount of code we can secure, okay? So it's lightweight. So I'm sure if you know IAGO attack. So this is a famous attack. Compromised operating system kernel can use manipulated return values from the system call to compromise applications. So this is very smart. So IAGO attack is like serious threats to applications if the kernel is compromised. So our design can defend against this type of attack because in our workflow, we can add additional integrity check before we return the values to the application. So additional security is added. So now back to your question. So let's go to see. Okay, so this is the workflow. Hopefully you can answer better or most of your questions. So basically you can see here. Now we have more detailed view to both worlds, okay? So for every processor design on x86, I think most of us can remember the ring levels, right? Ring 0, ring 1, ring 2, ring 3. Those are 4 different privilege levels, or we can also say those are different processor modes, okay? So if you look at here, so we have SVC, that's service mode. So you make system call, ARM processor goes here. ABT, that's abort. So basically, if you're accessing page not in the memory or invalid page access, that's abort mode. So IRQ is the interrupt processing mode here. So that's interrupt. So that's the user mode. If you look at the dash line here, above dash line is user mode. Below dash line is privileged mode. So actually, if you look at the ARM reference manual, so it goes so fast. If you look at the ARM reference value, depending on the model of the processor, it may have more processor modes here. But here, I'm just using this example to show for different processor modes, for different functions of processor, how we arrange the privilege levels here in our design, okay? So basically here, you see normal world. If we serve the application in the normal world using the service mode of processor here, we are going to have a problem because, like I said, if the kernel is compromised, then everything is compromised. So instead here, once we move our trusted application to the secure world, you see here, that's the monitor here we have in the secure world. And then you see the service will be done in the secure world. So once we have a service request or a system call, it will be done in the secure world using these paths. But the actual service, like I said, it will go back. Proxy will forward. Okay. So you see here, the secure world also have all the processor mode. Like the secure world will handle paging separately from the normal world. So paging is about virtual memory management. Basically, you access a memory page. If it's not in the memory, we need to map or load the memory contents and update the page table. So basically here, you see here. So in the secure world, we manage the page table. You see the abort mode handled, and the normal world abort. So these two page table management are separate. They are separate. So in case we have compromised the kernel in the normal world, the secure world paging will not be affected. So the memory management will not be compromised. Okay, so this is very important. So in addition to the processor mode isolation, we also need to think about the memory, how memory is protected in the case of compromised kernel. So here, this figure shows better, like I said, this is a secure world, this normal world, and like the memory management unit, MMU is for paging, right? So MMU we have two sides of paging. So one side is for secure word, one side is for normal word. So you see the different color here. S is for secure word, and in shadow. So so you see here, the zone isolation we consider like normal area. TZ is for trust zone, the secure word. Secure word is called the trust zone. So trust zone runtime, trust zone app. So basically you see that's how we map the memory space in the secure word and in the normal word, how they are overlapped, how they are divided. You see, we don't overlap the secure word and normal word, but we need somehow overlap. So I will explain why. So the reason is we don't want absolutely clean isolation. The reason is, think about system call. What do we need for system call? We need the parameters. If you have system call open a file, you have to tell which file you want to open, right? That's part of parameter. So basically, so let's play the slides here. But so I touched the keyboard. So go here. So basically, when we try to let's go to here. Is here. Okay. So from this figure, we showed we isolated the secure word and normal word. But like I said, if we consider system calls, we have to transfer some contents as the parameter. And we have to accept the result of system calls. The result sometimes is not only a single like number, sometimes is the contents in the buffer. Okay? So it's not easy, there is no easy way to just encrypt, decrypt, or not to share the parameters using like registers, using a fixed like array structure or something like that. So basically, we have to overlap only a little bit, a specific area of memory between the normal word and secure word to transfer the system call parameters and the result. Okay, so that's necessary. So here, when you look at the figure, it's not absolutely isolated between the secure word and normal word. We still have something. Okay, so some area will be used to transfer parameter and replies. Okay, so remember that. The next step, because we are having trusted applications, we are protecting the parameters, protecting the replies. Now we need to have additional protection about the application. So think about application. Because when we double-click application, the operating system is the guy who loaded the application. But I'm saying something sounds like a paradox or contradictory. We don't trust the operating system. Now I'm asking operating system to load my trusted application. How can we do that? What if the operating system changes my application during the loading process? That's disaster, right? So we want the integrity of the trusted process. So here, you see here? So we create a profile for each trusted process, okay? You see here? That's the example. So this is example. So this is the data structure. So if a programmer, you probably want to see the right bottom part, that's the structure. But the general idea is here. So basically, we generate the hash value, we add a signature to the application. So when the application is loaded, we check the signature to make sure the integrity of the application is fine, is good. Okay, so no changes, okay, not compromised. So this, but of course, adding the signature, adding hash value will require additional verification and the calculation when the program is loaded. Okay, so that's the key idea of how we protect the application. Of course, There are other issues, so memory, devices, interrupt handling, paging, but we don't ever have very limited time. So I can give you the references. You can read the further details there, but that's the key idea. Okay. Any questions? Yes.
Like, is it on? Okay. You said like you load the entire app into the secure world, which means it's a memory slot which is like not accessible to the user space, basically, sort of, right?
Right.
So, do you load like the entire app, like the app memory, into your secure world memory, or like only some pointers, or like some information of the app into the secure world? For example, like some important files, or like the password file, or you load like the entire memory into the secure world? How
That's
does
a very
that
good
work?
question. So there are a lot of issues involved here. So first, we still follow paging. We don't load the whole. I said the whole application. I'm saying whenever any part of the application is needed, it will be loaded. So we still using
So it will
paging,
be
like
like
virtual memory.
dynamic, not like the entire memory.
Oh yes, that's right. That's right.
Okay.
That's right. Correct. And also, you asked a very good question because you mentioned the keyword function. So for security purposes, there are some critical things or critical functions that cannot rely on any untrusted sources, like random number generator. So if you want this function, we don't even think about a compromised kernel. Forget about that. So some functions. So when I explained the basic ideas, I said all the system calls go to the outside, go to the normal world. Okay, we don't trust. I don't care. But actually, we care. We have several identified secure functions. Secure, not many, so only several. We rely on them for security work or for secure computing. So like I said, random number generator. So we don't rely on the outside world. We rely on the secure world. So we include that function inside the secure world. So that's a very good point. So we do consider those functions. So they are separated from the operating system kernel, then they're protected.
Okay. Okay, I got it.
Very good. Very good question. And yes.
Thank you.
Where is the process actually verified? Is that in like the runtime, or is it in the actual application itself?
Runtime.
Okay.
Runtime. So, but once when we load the application, we verify once. But after we load it, it's already in the secure world. We don't run it.
Okay.
So because due to performance issues, if we keep running it, so we are wasting our time, right? Yeah. Any other questions? Yes.
You made a great point that it's highly desirable not to force applications to be changed in order to be ported.
Mm-hmm.
What language should I use for application for your platform?
Oh, basically whatever language you are using now to develop applications, because like I said, these platforms will support legacy applications, no modification is needed. So keep whatever you are using.
So it's language agnostic. That's really great.
Because this is only a platform that doesn't introduce additional requirement to the applications.
Yeah, that's really great.
Okay, very good. So just quickly show you the evaluation. So this is a very popular benchmark to see the performance. We did other experiments, but just show you this is the major experiments to see. There are some other popular protection mechanisms like InkTag. They are very popular. Virtual Ghost. So you see the overhead here, 2.01. Then you see other numbers. So our system has you can see the overhead here, but compared with other system is lower, is much lower. And this figure shows for web servers, that's the overhead, HTTP server overhead, and this is the HTTPS in red color. So basically the highest overhead you can see 1.10. So that's pretty much acceptable. I mean, considering all the security benefits we have, right? And actually even better if you think this web server, who is going to run web server on ARM platform? So basically, it looks to me it's pretty acceptable to me. So so basically, our experiment is showing, so for those popular benchmark programs or applications, we are proposing or implemented very practical security mechanism on the ARM processors. So, okay, I think we have 1 hour, right? Just, I think 7 minutes left, right?
Usually they end at 5:20, but you can take.
Oh, okay, sorry. So, okay, any other questions? Okay, so just a quick, let me just give you some information of what we are continuing on this project. So like I said before, it's never be a perfect solution. So because trust zone is still isolation between two words. So when you enter trust zone, exit the trust zone, you are going to leave some information in the cache somewhere else in the memory. Those information left when you enter or exit transiting between the two words will create side channels. So attackers may utilize those information left by the application then to get some information from the application. So it's never absolutely secure. So our solution is only about the strong isolation, it's memory isolation, but is not a solution for side channels. So we are working on side channels. Basically, we look at what the information are left after we enter trust zone, then how they can be utilized. So that's a problem probably you are also interested in. So that's one possible research problems. Okay. So any other questions?
Thank you.
Okay, thank you. Thank you so much. Thanks for coming. Okay, thanks.